Hi, my name is Emily and I'm going to be going over problem number 4 on the 2009 Calculus BC FRQ. The problem gives you a differential equation dy over dx equals 6x squared minus x squared times y. You are also given an initial condition f of negative 1 equals 2. Part A asks you to use Euler's method, not that Euler by the way, with two equal steps starting at x equals negative 1 to approximate for f of 0. Part A asks us to find the approximation using Euler's method, and this is the formula I use, where y sub n is the nth step, the x and the y being plugged into the dy over dx, which is the differential equation, are points from the previous step of n, so basically the n minus 1. H is the step size, and the y sub n minus 1 is the same y being plugged into the dy over dx, which is the y value of the step before. We're going to let the step size be 0.5 because negative 1 to 0 with two steps of equal size would require each step to be a 0.5 increase. Our first step will be at x equals negative 0.5, so f of negative 0.5. This is because we added 0.5, which is one step, to negative 1 to show that it went up by that one step. The y sub 1 also indicates that we are finding the f of negative 0.5 approximation as the vertical height of our first step, so basically the vertical increase. The x and the y values being plugged into the differential equation will be points from step 0, which is the initial point, since we're finding step 1. We want to go back to step 0 and use those points. Conveniently, the initial point is given. We plug in negative 1 and 2 to the x and the y, respectively, in the given differential equation. This gives us 4. Then we multiply that value by 0.5, which is our step size h. Then add that value by the initial y, which is 2. It is the same 2 that we plugged into the differential equation. By doing this, we get a y sub 1 approximation of 4 when x is equal to negative 0.5. The point we found is now negative 0.54. So basically we can say our approximation went from negative 1, 2 to negative 0.5, 4. But we aren't done because we need to find the approximation for when x is 0. This means we have to repeat this process once more to find y sub 2, which is our second step. When we plug in the point for the first step into the differential equation, since we are looking for the second step approximation now, we get 0.5 once doing all the calculations. Then we multiply that by 0.5, which is our step size. Then we add the y sub 1, because that is the y value of the point before the step size we are approximating for. Doing this, we get an answer of 4.25, which is our y sub 2 value, and also our approximation for f of 0. Part B asks for the second degree Taylor polynomial for f about x equals negative 1 if the value of the second derivative at the point negative 1, 2 is negative 12. All we need to do is remember the Taylor series format. This question asks us to find the polynomial, which is a partial sum instead of an infinite sum up to the second degree. This means we just need to list it until we get to the x term to the second power. Now we need to find f of a, f first derivative of a, and the f second derivative of a, where a is the center negative 1. We have already been given f of negative 1, which is 2. We can calculate the first derivative of f at x equals negative 1 by using the given point negative 1, 2, and plugging it into the differential equation dy over dx, which is the first derivative equation. This gives us 4. And note that we have already been given the second derivative of f at x equals negative 1 in the problem, which is negative 12. Always read the problem carefully to avoid doing unnecessary work. Plugging in the values we found into the Taylor series format gives us this expression. Simplifying this gives us the expression 2 plus 4 times x plus 1 minus 6 times x plus 1 squared. This is our second-degree Taylor polynomial for the function f centered at x equals -1. Part C asks for the solution y equals f of x to the given differential equation with the same initial condition, f of -1 is equal to 2. The dy dx we were given is 6x squared minus x squared times y. We want to split up the x and y terms first, so we want to first factor out the x squared. Dividing 6 minus y and multiplying dx to both sides gives us 1 over 6 minus y dy equals x squared dx. To get rid of the dy and the dx, we want to integrate both sides. Using integration rules, we know 1 over 6 minus y will be ln of absolute value 6 minus y, and then made negative because of the minus y inside. On the other side, with the x squared, we can incorporate power rule but do it backwards. When we take a derivative using power rule, we normally bring down the exponent and subtract 1 from the exponent, but for integrals, we can just add 1 to the exponent and divide by the new exponent value. This is anti-deriving. Note that this is only convenient for simple integral expressions such as this, with the x to some power. If there are more complex things like trigonometry or logarithmic functions involved, it is best to use u substitution or integration by parts, or even trig sub if necessary. Integrating x squared gives us x cubed over 3. And do not forget the plus c that acts as an unknown constant after integrating an indefinite integral. At this point, you might be wondering why the question specifically reminded us of the initial condition f of -1 is equal to 2 in part C when it was already stated in the original problem. The plus c is exactly why. We need to find c using this initial condition. We can plug in -1 to x and 2 to y, which after some simplifying, gives us c equals 1/3 minus ln 4. We can now plug this back into our original equation that we found. This is what we get after plugging in the c. Remember, we are trying to find y equals f of x, so we need to isolate the y. So we have ln of absolute value 6 minus y equals -x cubed over 3 minus 1/3 minus ln 4 after multiplying both sides by a negative, to get rid of the negative that was in front of the ln. Now to get rid of the pesky ln, we can put everything to the power of e, because e to the ln power cancels each other out. Then we can get 6 minus y equals e to the -1/3 x cubed minus 1/3 plus ln 4. I know this is a lot, but we're almost there. Now we can manipulate the equation a little to put y alone, like moving the 6 to the other side and multiplying both sides by a negative to get rid of the negative sign in front of the y. This will finally give us y equals -e to the -1/3 x cubed minus 1/3 plus ln 4 and plus 6. And you're done. For more practice on problems like these, try solving the 2007 Calc BC FRQ Form B number 5, as well as number 5 on the 2010 BC FRQ. Note that number 5 on the 2010 FRQ requires a negative step size, so make sure you are able to recognize that in the Euler's method problem.